In this video, we're going to talk about allylic bromination of alkenes using NBS. NBS stands for N-bromosuccinimide. NBS has a weak nitrogen-bromine bond that can cleave in the presence of light and form two radicals, a radical on the nitrogen and bromine radical. NBS then reacts with allylic or benzylic positions to give allylic or benzylic bromines. Allylic positions are positions right next to double bonds, so we can replace any of those green hydrogens there with a bromine. A byproduct of this reaction is shown here. Here's an example of a benzylic reaction with NBS. Heat is used to cleave that nitrogen-bromine bond, and then we get reaction at that benzylic position to give two possible products. In this case, we have a new stereocenter that's formed, and we see that both configurations are produced, or we end up with a pair of enantiomers. Now let's take a look at the mechanism. As I mentioned, the nitrogen-bromine bond is weak, so it undergoes homolysis or homolytic cleavage to form a radical on that nitrogen and bromine radical. The radical on the nitrogen doesn't do much after this because it's resonance stabilized. You can imagine that you could draw electrons here and get a resonance structure. Where the radical is up there on the oxygen. Bromine radical can then react with our allylic or benzylic hydrogen in an SH2 or hydrogen atom abstraction mechanism. This generates HBr, which reacts with additional NBS in a proton transfer step. The resulting Br- can continue to react and give us just a little bit of bromine. You'll notice that it says that there's a low steady concentration of Br2, and we want to make sure that this is a very low concentration. If you get too much Br2, then you will react with the alkene. If you remember from way back when, addition of Br2 to an alkene gives you two bromines with anti-addition. Hopefully that sounds vaguely familiar. The important part here is formation of the bromine radical. So let's see how that reacts in our next step. You can see that bromine radical then can react with our allylic radical. So this is how this would work here. And that gives us the allylic radical shown here. The allylic radical is very stable because it's resonance stabilized. The resonance structure that you can get from that allylic radical. You can imagine there are a couple of ways then to get to the product shown. You could get just bromine radical coming in and reacting. You can also get that small amount of Br2 coming in and reacting. Let's show how that works. So this type of mechanism here would give the product shown along with some more bromine radical that could go ahead and continue on in the reaction. It's important to note that in this particular reaction, we have a symmetrical molecule in that both of these resonance structures are the same. Here's an example of a reaction of a non-symmetrical alkene with NBS. Okay, here's one octene, and it will react to give an allylic radical. Which is the same as the radical shown here. Now there are two possible options. One, the bromine can add in directly. And that's going to get you this product over here. The other option is that resonance occurs to give the radical shown here, which is the same as this one here. The bromine adds in there, then we get this product here. And you can see actually that that happens to be the major product formed. This is related to alkene stability. We are getting an alkene that is di-substituted as opposed to an alkene that is monosubstituted, and the di-substituted alkene is more stable. You also see a slight preference for trans in this case. Here's one more example. We can see that either the green hydrogens can react or the blue hydrogens can react, and each of those have possible resonance structures. Let's draw that out. And that radical there leads to this first product on the left. It also has a resonance structure. And that resonance structure will give you that second product there. What happens if one of the blue hydrogen reacts? Well, the first radical here will lead to this one shown here. And then it also has a resonance structure that leads to this rightmost structure. And now we can see that because we have a non-symmetrical alkene with two different allylic positions, we can get 4 products.